Okay, so this is the last video in SC14 and it is on the molar volume of gases. So hopefully you recognize the diagrams that I've drawn. They are particle diagrams to represent a solid, a liquid and a gas. And you should be familiar with the fact that the particles in a gas are much further apart than the particles in a liquid or solid, and this is because the attraction between the particles in a gas are much weaker than the attraction between particles in a solid. So when we did structure and bonding, we saw that ionic compounds are typically solids at room temperature because there is a very strong electrostatic attraction between those oppositely charged ions. And then later on, we saw that simple molecules were typically liquids or gases at room temperature because there were only weak intermolecular forces between the molecules. So gases, there are only weak attractions between the particles. For that reason, they tend to be much further apart. And underneath, I've just drawn, let's just say that this container is like a 5-litre container. And into this 5-litre container, I pump in 3 molecules of H2. And into this 5-litre container, I pump in 3 molecules of NH3. So NH3 is a bigger molecule than H2. All right, I've got 4 atoms instead of just 2, and I've got an extra hydrogen as well as a bigger nitrogen. So my NH3 is considerably larger than my H2, but it doesn't matter what the gas is, they're going to behave in the same way. If I pump my 3 molecules, which is obviously tiny, into my big 5-litre container, what's going to happen is each of my H2 molecules are going to spread themselves out as far away from each other as possible, and my NH3 molecules are going to do the same. Okay, because gases, the particles in a gas will spread out and they will fill all the space of the container that they are in. So this is quite different to liquids or solids. If I was to pour a solid into this container, the solid would just collect here at the bottom. If I was to pour liquid into this container, again the liquid would collect at the bottom. But gases, they take up as much space as possible and they will totally fill the container that they are in. And it doesn't matter what gas it is or how big that gas is, they will all act in a similar way. So this is when I'm pumping a gas into a kind of a confined space. But what if I had a gas, in a much larger area? Just how much space will a gas take up? Well, we have to remember that even though the forces between the gas molecules are weak, there is still some attraction between those molecules. They're intermolecular forces, and yes, they are weak, but they are still present. So they're not going to completely separate from each other unless you've got some sort of external factors, like if you release a gas outside and you've got wind that can blow the molecules far away from each other, and that's an external factor that will affect how the gas molecules behave. But if you have it in a kind of controlled environment and you release a gas into a kind of a large open space, yes, they will spread out from each other, but they are still attracted, so there's only so much space that they will take up. And what they've seen is that if you have 1 mole of a gas, so let's just say you've got 1 mole of H2, that the space that 1 mole of H2 takes up is exactly 24 decimeters cubed. Okay, so that's 24 litres. So it's quite a large area, 24 litres. So just to remind you, if you've got 1 mole, so here I just drew 3 molecules of H2, but if you've got 1 mole of H2, you would have 6.02 by 10 to the 23 molecules of H2. So far more than I'm willing to draw. So 6.02 by 10 to the 23 molecules of H2, it would take up 24 decimeters cubed if you had it in a controlled environment at room temperature and at room pressure. So you don't have high temperatures or low temperatures or extreme pressures or any kind of other external factors like wind or any of the rest of it. That's how much space it will take up. But similarly, if I had 1 mole of ammonia, so 1 mole of NH3, it will also take up 24 decimeters cubed. And remember, if you've got a mole of H2 and a mole of ammonia, mole is just a word that represents a number. The number it represents is 6.02 by 10 to the 23. So even though ammonia is a larger molecule and you might expect that it would take up more space than H2, it doesn't. It takes up the same amount of space. If you've got an equal number of molecules, if you've got 1 mole of both of them, they will occupy the same space, even though NH3 is bigger. And that's true of even larger gases. So if I have a mole of propane, which is C3H8, so I'm going from just having 4 atoms in my molecule of gas to having 11 atoms in my molecule of gas, so it is a good bit bigger. Again, it's still just going to take up 24 decimeters cubed, or 24 litres, at room temperature and room pressure. So all of those gases will behave in exactly the same way. They will spread out away from each other to take up space, but they are still attracted to each other by these weak intermolecular forces, so there is only so much space that they will occupy, and all gases, regardless of their size, will occupy the same volume. So 1 mole, no matter which gas it is, will occupy 24 decimeters cubed. And this number 24 is what we call the molar volume, and it's a quantity, a number that you're going to have to learn. The molar volume, which is the volume that a mole takes up, regardless of what gas it is 24. And you can have it as 24 decimeters cubed, or if you were to put that in centimeters cubed, it'd be 24,000 centimeters cubed. And from this, I can write my final formula triangle, where I put volume at the top, I put moles at the bottom, and I put what I called Vm, which is the molar volume, at the bottom as well. And I'm going to show you some examples of how this is used by going to your booklet. So in your booklet, I've just written out a brief explanation, and I've got that same triangle, and then I have some examples. So I said a sample of CO2 occupies, so I have given you, and again, it's really important that you can read your units and you know what you are being told. So you're told that it occupies 3,200 centimeters cubed. You are being told the space or the volume that that gas is taking up, and they want to know how many moles of gas are present. Well, using my formula triangle, if I've got the volume, and this number here, the molar volume, is always 24, so I've got volume, I know this is 24, so moles is going to be volume divided by 24. So again, I said the 24 was in decimeters cubed. The volume in my question is in centimeters cubed. So what I'm going to have to do is I'm going to have to take that volume, divide by 1,000 and get it into decimeters cubed. And then moles is just going to be the volume that I'm given in the question divided by 24 equals the moles. So that is always going to be 24. It's called the molar volume. So if I had 1 mole of gas, it would be taking up 24 litres. This is telling you that you know the volume. You can see that it's much, much smaller volume than 24 litres. It's only 3.2 litres. So I know I don't have a full mole of the gas. And if I do 3.2 divided by 24, I will see that I only actually have 0.1 moles of CO2. Another gas here, hydrogen chloride. Remember, I'm only calling this an acid if it's AQ, so it's G, so it is a gas, and I'll be calling it hydrogen chloride, not hydrochloric acid. And it occupies 4,000 centimeters cubed, or 4 decimeters cubed. So again, not occupying as much space, so I know I don't have a full mole. I must have less than a mole because it's occupying a lot less space. So I need to figure out how many moles do I actually have. First thing I want to do is I want to get this into decimeters cubed, so I divide by 1,000, and then again I'm dividing by that number 24 to find out the number of moles that I've got. So I've got some practice questions for you. So when you are calculating the number of moles of the volumes below, change your volumes, all of them, into decimeters cubed, and then you're just dividing by 24 every single time. All gases take up the space 24 decimeters cubed at room temperature. So you're always dividing by 24 regardless of the gas. In question 2, I ask you to calculate the volumes occupied by the given amount of moles. So we said if you had 1 mole, it would occupy 24 litres. If you've got 5 moles, it's going to be 5 times 24. So in these ones, it's going to be the number of moles times 24. So you're going to take the number of moles, no unit conversion is necessary, times it by 24, and you're going to get the volume that's occupied. Okay? Then at the end, I kind of combine a few things. So I'm just going to go back to my piece of paper for a second. We've now come across 3 formula triangles. One with volume, moles, and molar volume. Remember, that's a constant, 24. The first one we had was mass, moles, and formula mass. And then the other one we had in a previous video, we had moles, concentration, and volume. So they're the 3 kind of formula triangles that you need to know. If you look at the formula triangles, there's only one that is consistent across all 3, and that is moles, which means you will always be able to calculate moles, and once you've got moles, you can move on to a different triangle. So for example, if they gave you concentration and volume, but they wanted mass, you would use the concentration and volume to find moles, and once you've got moles, you can find mass. If they gave you volume, just volume, and you wanted mass, then you'd be using this triangle. You'd find moles, and then you go over here, and you would find mass. If they gave you mass, and they were looking for concentration, then you would, oh no, sorry, scrap that, you still need volume. If they gave you mass, and they were looking for volume, then you would use this triangle, find moles, and then come over here and use this one. So whatever they give you, use the appropriate triangle to find moles, and then you can move on to a different one. Now you'll see that volume is in both of them. Okay, it should be obvious though which triangle they want you to use. If they only give you volume and nothing else, you're going to use this triangle because you can always get molar volume because it's always 24. So if it's just volume, nothing else, then this is the only triangle that you can use because this is always going to be 24 and you can find moles. And again, typically this is going to be when you're talking about gases, all right? If they want you to use this triangle, then they're going to give you volume and they're going to give you concentration, and you're going to be using this triangle when you're talking about solutions, okay? So it should be obvious from the information they give you which triangle they want you to use, but make sure you know all 3. And then again, sorry, with this one, you can always find formula mass using the large numbers on your periodic table. So if we have a look at some of the practice questions here. So a reaction generates, so I'm giving you the mass of carbon dioxide. I want to know the number of moles. Okay, so it's going to be mass divided by formula mass equals moles. Once I know moles, they want to know the volume. Okay, so I've used mass divided by formula mass to find moles. Then they want me to find volume. They're talking about a gas, carbon dioxide, not a solution, and they haven't given me a concentration. So I'm not going to go over here. I'm going to go over to this triangle. I've just found moles. I multiply by 24 and I find my volume. A different reaction, so I've given you a different mass of a gas. Again, you're going to do the same thing. You're going to find the moles of nitrogen gas. Once you've got moles, you multiply by 24, it gives you the volume. Last one here, again, I'm giving you mass. I ask you straight away for volume, so you're going to have to go from mass to moles and from moles to volumes. Again, because I'm talking about gases, you're going to be using this here to find volume. And then again, yeah, it's the same kind of thing. Okay, so you're going to be doing these questions for me. And again, once you do the questions, you can check your answer. All of the answers are there at the back. Just make sure that you're not just obviously copying my answers, that you're doing it for yourself. And then you're checking them. You've also got all of the exam questions. I'll try to put them in order this time. So I've gone for kind of theoretical yield and percentage yield questions first, and then we move on to some atom economy questions. Then I put in some concentration, and then it moves on to titrations and titration calculation questions. And you can see that there's a lot of questions on the titrations and a lot of marks going for those titration calculation questions. And then at the end, Right, at the very end, you have a few questions on volume when they want you to use that number 24. And when they want you to use it, they give it to you. So 1 mole of any gas at room temperature and pressures occupies 24. So they do give you that information. It's obvious when that is the triangle that they want you to use. So yeah, we'll be having a go at these exam questions. So they're the exam questions from 2018, 2019 and 2020. So there's only been 3 years of this new specification, and all of the questions on this topic that have come up over those last 3 years, I've put them all in there for you, and the mark schemes are at the end. So again, any questions on all of this? I know these calculation topics can sometimes be a little bit tricky, so any questions on them, please just message me and let me know.